Okay, so we're starting with we're going to derive our kinematic equations, assuming constant acceleration. That's a big assumption. And no, I didn't mention that before. Yes, we need to assume constant acceleration for what we're doing today. Okay, so given that I walk at about 2 meters per second across campus, I've got long legs. Tall people can walk faster, and I do this for 5 seconds. Well, what is my displacement? Well, we can pretty much eyeball that one, and we'll know that it's 10 meters. Okay, duh. But we're going to solve it, and we're going to do this rigorously. So we know the v equals delta x over delta t. Okay, which means delta x, if we multiply the delta t over, delta x equals velocity times our change in time. All right, and so what is our initial time going to be? Well, if we go from when I start walking, okay, our time will be 0 seconds, which makes ti go to 0, okay, and then leads us to, what is our t final? Well, if our total time was 5 seconds and we're subtracting 0 seconds from it, then our total time, our final time is also going to be 5 seconds. Okay, so delta x equals velocity times time, 2 meters per second, times 5 seconds equals 10 meters. Simple. But we like to graph this, so let's see what it looks like on here, and this you'll see what we're getting at here in a bit. Okay, so 1, 2, 3, 4, 5 for time, and velocity in meters per second is 1 and 2, so we graph this, and we get this. This is what our travel looks like. This is what the particle that is moving at 2 meters per second for 5 seconds will look like on our velocity time graph. But what is its acceleration here? Is it a constant?
Yes.
It is a constant. What can we tell about this graph? What can you tell me about the shape of this guy right here that tells you that we have constant acceleration? Okay, it is flat. Okay, or more to the point, it is straight. That there's no curve to it. Yeah? So it is constant. Yes, it is constant. However, what is its value? The value of the acceleration is not only constant, it is constantly what? It is 0, and we can tell that because the slope of the line is 0. The slope of a line is 0, and so we're not Cool, I like that better. Okay. The slope for a line is 0, therefore acceleration is going to be 0. It is 0. We're going to erase all that. Okay. Now, if we draw these lines, if we create these boxes underneath our graph, okay, how many squares are there? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares, right? There's 10. What do they represent? Okay, each square represents 1 meter per second times 1 second, and so each square is a representation of 1 meter of displacement. Yeah? That make sense? Yes. Okay. So that leads to the area, the total area here underneath the velocity time curve equals our displacement. So all that right there, if we measure the area of all that, okay, all this stuff right here, this is all our displacement. Now, some of you may already be seeing where we are going with this, okay, but let's keep that a secret for our next lecture, because we're going to hit that later on today. All right. That whole thing represents delta x. There's our graph again. All right, so what if our velocity then is increased from 0 to 2 meters per second during those 5 seconds? So if we have a changing velocity, okay, so that's from 0. In fact, let me step back a little bit. If we go from, okay, there's our 5, our 2 meters per second, 5 minutes, and we know we're starting at 0. Okay, and we draw that line in there. How much did we change our position? What is our displacement? Okay, because the first time we were just timing, it was a clocked time, starting 2 meters per second, finishing 2 meters per second. This one's different. This one, we are actually starting at 0 and traveling up here to 2 meters per second. Okay, we're going to use the concept from the previous slide. Okay, so we'll fill in that little area. And let's count that area. And then that one, which is more. So after 3 seconds, we're taking more and more displacement as we go on. Okay, and then from 3 to 4 seconds, it's a lot more. And then 4 to 5 seconds, it's a heck of a lot more than what we had before. But what we have here is a triangle. And with the triangle is really half of a rectangle, isn't it? Okay, so we cut it in half. And so, okay, now mind you, this is again assuming constant acceleration. Okay, assuming constant acceleration, and the slope of the line from our previous lectures, that slope is our acceleration, which is getting us to, we've got a big idea coming up, a really profound concept. Okay, so we're going to do this qualitatively. Okay, we have an initial velocity. We will call it v naught. Okay, and we increase over a certain length of time. Okay, and we know that our line is given to us by y equals mx plus b. Right, that's our analytic geometry version of the line, but we don't use y equals mx plus b in here. We use, okay, our velocity equals, okay, there's our slope, right? It's the delta v and delta t. So that's going to be, okay, we know that delta v over delta t equals, go ahead, guys. It's what? Go ahead. Okay, so yes, delta v over delta t equals our acceleration. All right, so the slope of our line here is our acceleration. We multiply it by time, because that's going to be our x variable, right? Plus our initial velocity, because that would be our y-intercept, right? Our velocity intercept would be v naught. Okay, so here we have this v equals at plus v naught is, okay, or actually by convention we rewrite it. We put v naught plus at in physics. That's just how we do it by convention. Okay, v naught plus at, and this is our kinematic equation number 1. V equals v naught plus at. We're there. Congratulations. Okay, we did this qualitatively. We've come up with, okay, where v equals v naught plus at is really just y equals mx plus b, except we're actually using it now. All right? And so, there it goes. We put it up there in the corner. Right here. Here is equation number 1. And we're going to move on. So, let's find delta x. Oh, look. What do we have here? We have a shape, okay, where we have this side is parallel to this side, and this is not parallel to this. This is called a trapezoid. Okay. So we're going to want to find this whole area. Okay, this is a trapezoid. And what is its area? Oh shoot, I meant to put a stop in there. Back. Stop. Go. Okay, so the area is the average of the base. Oh, you are going too far. What are you doing? All right. The area is the average of the bases divided by the height, or base 1 plus base 2 times the height. Now, what are the bases here? Okay, the bases are the parallel ones. That's how we determine a trapezoid. Base 1 and base 2 are the parallel sides, and the height is the perpendicular distance between those two. So what that really winds up being is that this is a base here, and this is our other base here, and this is a perpendicular height between the two. So this is going to be V naught, right? And what's our other height going to be? What's our other base going to be? This value is V, yeah, whatever velocity we're finishing at. Okay, so this is going to wind, our delta x, which is this area down here, is going to wind up being V naught plus V, right, because those are the two bases. Both of those divided by 2.
Would it be VFT?
We're just calling that point, we stop at some velocity V, whatever it is. Okay? And the height in this case is going to be T. Okay, so now we have our displacement equaling the average of the velocities times time, and that is actually our second kinematic equation. Okay, and we put that second equation right there. Okay, so yay, we have equation 1 and equation 2, and we're going to move on. Okay, now, this next one is the one I call the granddaddy of them all. This is, oh, that's not what I wanted. Yes, this. I'm not sure if this records, if it's a screen recording or a pad recording, so I just showed a picture of my daughter as the granddaddy of them all. There we go. So, we are going to substitute equation number 1 into equation number 2. Lovely! We love doing algebra games. So, we know that delta x equals V naught plus... Okay, so you guys see that? We took V... Oh, that's not what I wanted. We took this V, and plugged it into here. And so we're getting V naught plus AT, right? Because that's the equation 2. Plus V naught. So this remaining V naught right here. Okay, and we finish the equation. So we plug 1 into 2. You guys see that substitution there? All right. Okay, and that equals 2 V naught plus AT over 2 times T. Which winds up being, so we simplify, so we get, so the 2's cancel here, and we got the 2 staying under that one, so we get V naught, and then we multiply it, we distribute the T. So it's V naught T plus 1/2 AT squared. Yeah? Okay. that is equation number 3. Woohoo! This is the one I refer to as the granddaddy of them all. I do want to do a little bit of housework here. I want you guys to make sure that we remember that delta x is really x final minus x initial. X final minus x initial can be written in a different way. And you will sometimes see just x minus x naught as as the same thing. You guys see that? It's whatever x we're at minus what we started is x naught. And this x naught will get put in here. X naught plus v naught t plus 1/2 at squared will give you x. Do you guys see how those are pretty much the same thing? Okay, so you will sometimes see that equation as x equals x naught plus v naught t plus 1/2 at squared. Okay, that you will sometimes see it like that. I'm not going to show you like that anymore, though. So we're going to get rid of all that. Wipe. Okay, so that is equation number 3, and that will join us over on I don't remember what that is right there, so that's ugly. Okay. All right, so if we solve number 1 for t, solve the first equation for t, we're going to get t equals v minus v naught over a. Yeah? Can you guys see that? V minus v naught over a. Okay, and we are going to plug that into number 2, okay, in a different way. So instead of substituting velocity in for velocity, we're substituting the time in for the time. Yeah? Okay. That gives us this delta x here times v naught plus v over 2, right? Times this new term, which is our v minus v naught over a. Now, you guys, being smart algebra students or calculus students, something should be blaring its horn at you right now. Difference of squares. Yay! V naught plus v, v minus v naught. If we flip these two, it looks better. If we flip these two, it looks better, but it is difference of squares. What's the great line from what the Matrix movies that comprehension is not requisite for compliance? You don't have to understand to do what I tell you to do? Yeah, okay. All right. So we get our displacement is v squared minus v naught squared over 2a. Now, because we don't like a whole lot of fractions in these, even though 2 of them have fractions, now mind you, this is a perfectly fine equation. We could be using this, but this is a colossal pain in the publisher's rear to typeset over and over and over again. So they don't, and we want to write them as close to one line as possible. And so we get v squared equals v naught squared plus 2a x, or plus 2a delta x. And that is kinematic equation number 4. So now we have these 4 kinematic equations. And they're there. And we'll keep them off to the side, and we're going to do some samples here. Okay, so let's take number 1, and number 2, there's number 3, there's number 4, all right? 1, 2, 3, and 4. Yes, write them again. Because we're going to make a chart here. This is a handy little guide for how to use these. Then do that. All right, so we make this chart and we write our equations in it. And notice, stop. Go back. Giving away the plot. Okay. Delta x. Delta x is not present in the first one. Displacement is not present in the first equation, but it is in the other three. So when you are looking at what values you're given or what information you have to do your problem, if you don't have displacement, you're probably going to use the first equation. Okay, acceleration. Does the first one have acceleration? Yep. How about the next one? Nope. How about the next one?
Yes.
Yep. Yep. For the last one? Yeah. Okay. Velocity. Is velocity in the first one? Uh-huh. Is it in the second one? Yes. Is it in the third one? No. Is it in the last one? Yep. Okay. What's the last variable that I'm going to use? T. Time. Is it in the first one? Uh-huh. Is it in the second one? Yep. Third one? Uh-huh. Fourth one? No. Now, what about V naught? V naught is in all of them. V naught is in all of them. In fact, you have to have V naught for all of them. However, there's good news. The good news is, what's that? It will always be given, or it will always be implied. And this is the good news. The good news is, very often, you are starting from a standstill, which means your initial velocity is 0. Very often, V naught is 0 meters per second, which makes your calculations very nice, because that minus part goes away. Okay? And so that is it for our kinematic equations. And we'll pause there, or we will stop there.